Well, good day, folks. Thanks for dropping in to listen to this presentation about mountain water towers in the Bredor. Now, you may wonder, mountains in Cape Breton, Unama'ki, where did that come from? Well, here's a good example. This is Kelly's Mountain on your right, and it's acting as a sentinel on the west side of the major Great Bredor Channel, which brings you into the UN Biosphere Reserve. Now, when you think about mountains, this is probably the image that you're familiar with. This is the bugaboos out in the Rocky Mountains. High mountains, ragged peaks. But what's interesting in terms about mountains and water towers is this. 2 billion people worldwide depend on mountains for food, hydroelectricity, timber, mineral resources. About 40–50% of the world's population rely on mountains for fresh water. Mountain stream flow is about twice what you'd expect from the surface area, and it releases that snow and water in a favorable way to the lowland adjacent populations. Interest in mountains really started in 1965 with global recognition. 1992, the UN stressed sustainable mountain development. 2001, they launched the Mountain Research Initiative. 2002 is the International Year of Mountains, and there's ongoing research such as the Canadian Mountain Network Research Group. Just a curious twist there, the floodplains along China's Yellow River, Egypt's Nile River, India's Ganges River, and Babylon's Tigris and Euphrates rivers, which draw a lot of their water from the mountains, they cradled the world's 4 oldest civilizations. But it led to the ancient Chinese proverb, to rule the mountains is to rule the waters. And if you look what's going on right now between India and China and their problems in the Himalayas, well, the Himalayas is actually regarded as the third pole. There's this much snow in the mountains that pumps water down into quite a number of these large river systems. Okay, back to Kelly's Mountain again, and we'll use this as our table of contents slide. So I'm going to try and answer 3 questions for you in this talk. First, how were Cape Breton, Unama'ki's, the UN Biosphere Mountains formed? Secondly, why are they important to us as water towers? And thirdly, so what are we doing to better understand them? Okay, so let's tackle this first one, see how we make out. Now, just to give you a heads up, there are 4 main languages in Cape Breton right now: English, French, Mi'kmaq, and Gaelic. But now, through this presentation, I'm going to introduce you to a next language, and that's the language of rocks. So you better keep a pen and paper handy, because we're going to be going through some terminology and some texts, and you never know. You might just get in your email the next day, you might get a test to see how well you've learned your new language. Okay, North America is essentially formed by 3 big mountain chains over geological time. The oldest one, 1.8 to 2 billion years old, is called the Trans-Hudson Origin. Second oldest is the Appalachian Mountain Chain, between 300 and 400 million years ago, and that's where Cape Breton resides. And the most youngest one is the one you hear most about, and that's the Canadian Rockies, or the Canadian Cordilleran, which is between 60 and 100 million years old. Now, let's take a look at exactly how the Appalachian Mountains formed. So you might be familiar, hopefully are familiar with plate tectonics. So 400 million years ago, this is what the plates looked like. And where we now have the Atlantic Ocean, back then there was what was called the Iapetus and Rheic Oceans. And these 2 plates were coming together, converging. Cape Breton was roughly in the middle. Now, if you took a cross-section through there, you would get this sort of diagram. So I'm going to color code this. So the land on the other side of the ocean in green, the land on this side in orange, and the zone in between was where all the action was going as the 2 plates collided and one dove underneath the other. By about 340 million years, things were tightening up, things were converging. If you took a cross-section, you would begin to see this action. And as it gets narrower and narrower, you're getting into sort of a crunch zone, and lots of volcanoes, earthquakes, and faults. Now, you may just want to keep your handle on that Iapetus Rheic Oceans that may appear on the test. Like 270 million years ago, the plates had collided, and we had the Appalachian mountain chain formed, and Cape Breton was right in the middle of her. So that's what that cross-section would like. Mountains thrust up, a lot of faults going on, a lot of volcanic activity. Now let's see if we can put Cape Breton in that context for you. So if you remember, I painted the land on the other side of the ocean green. Well, here it is in Cape Breton, the whole southeastern part of the island and the southern part of the UN Biosphere Reserve. The land on this side of the ocean is up there in the northern tip, so Pleasant Bay, Bay St. Lawrence, Meat Cove. The crunch zone, that was just pretty much the rest of Cape Breton. So you can see we were in a pretty active region of mountains being formed. We also have another interesting aspect called telescoping of terrains. Ooh, that could be on the exam. And the reason for saying that is in this crunch zone, if you looked at the width of it to our north and south, it's about 200 to 300 kilometers wide. But in Cape Breton, it's only about 70 kilometers wide. So you can really begin to see the amount of activity that was going on in our island way back then. To begin to understand some of the resultant structures we find in our island, we'll go to this particular diagram. So as plates converge, sometimes you get what are called strike-slip fault zones. In other words, the land is sliding past one another. That could be another one on the test. But sometimes what happens is that, well, let's look at the Rocky Mountains as a good example of some of these. So that strike-slip fault zone, that would be similar to the San Andreas Fault you've heard so much about moving through California. Yeah. Along with that, you may get thrust faulting, another good one for the exam, where instead of sliding, it's thrusting big blocks of mountains upwards. Now, a good example out in the Rockies, if you've been at Banff, you've got Sulphur Mountain, big slabs of rock thrust up to create mountains. The third thing that's of interest is that as one plate slides down underneath another, as those rocks get moved down to depth, because of the high heat and pressure, the rock becomes molten and it moves upwards into magma chambers. This is hot molten rock that would be 600, 800 degrees centigrade. Some of those sort of reside in the crust, but some of them actually make their way up to the surface and they explode into volcanoes such as Mount St. Helens. Once all this activity is finished, then the mountains start to erode and they gradually start to wear down. And the sediment that's eroded off those mountains gets sent out by rivers and streams into the adjacent areas, and they form what are called sedimentary basins. You got to mark that one down. Okay, so what are exposed then are the roots of those old big mountains. And if we look at those roots, sometimes you might see those magma chambers, which have now been solidified into what we call granitic plutons. On top of that, you might see those old faults now exposed at the surface that created either those strike-slip faults or thrust faults. Okay, let's try and see if we can put that in perspective for Cape Breton. Now, this is a landside image, so this is showing the forest cover and the drainage. What we need to do is sort of strip off the vegetation, what's called a digital terrain model. So this is a black and white image that strips the vegetation off so we can actually look down and see all the topographic relief on the island. So let's load up. This is the Bredor Lake watershed, so this becomes the UN Bredor Lake Biosphere Reserve. Now, as I mentioned, as the mountains eroded down, the rivers moved all that sediment out into the adjoining lowlands called sedimentary basins. So this brown area identifies where those sedimentary basins are on Cape Breton. You also remember that what I said is that they didn't cover all of the roots, so there's still some roots open, and if we looked at those roots, you might see those granitic plutons, the old magma chambers that have now been solidified into rock. And here they are in red. We have over 100 of them on the island, so you can really begin to see this was a crunch zone time. Now, you may say to yourself, that's sort of neat, but is there some place on the island I can actually go and stand on them or see them, or maybe even feel the rocks or kiss the rocks. And I'm not sure if you want to kiss the rocks. You have to be fluent in rock talk before you get to do that. But at least you can begin to get the initial part of it. So if you're asking that question, the answer is, if you've ever driven around the Cabot Trail, yep, you've stood right on one of these. And I'm going to take you to Smoky. So there's the Cabot Trail running from one side of the picture to the other. If you went to the left, you'd go to Sydney. If you went to the right, you'd go to Ingonish. And in the middle, you'll see that's the provincial park coming out. And if you're standing in that park, you're probably looking out towards the North Atlantic and thinking what a nice view is, not knowing that you're standing on the roof of one of these big granitic plutons. And that pluton's exposed to a depth of at least 255 meters, and it goes much deeper than that, and it runs at least 15 kilometers at the surface. Now, what I said was that you couldn't kiss the rocks, but here you can taste the rocks. Because if you go to that provincial park and you drink the water that's supplied there, well, that comes from a drilled well drilled into that granitic pluton. And as rain falls and it filters through the rock, it's picking up some of the chemicals of the rock and creating its own taste. So you can actually taste the granitic pluton. So this is just another aspect. You hear about wine tasters, that wines have a certain taste, or bottled water of a certain taste. Well, now you can taste a granitic pluton. So now, next time you take some friends around and you're showing them Cabot Trail, take them out there and explain all this to them. That's really going to impress them. I also said if you're looking at the roots of those old mountains, you'd probably see the faults. Well, here they are, quite a number of them. Again, we were in the crunch zone. Now, if you also remember, we talked about those strike-slip faults, such as the San Andreas. Well, Cape Breton has its own San Andreas fault system. Runs up the west coast of the island, only we call it the Hollow Aspy Fault System. It extends underneath the Cabot Strait. It goes right through Newfoundland. And way back when the Appalachian Mountains were formed, Scotland was on the other side or north of what's now Newfoundland. And the number of geologists believe that this big strike-slip fault system probably shows up in Scotland as the Great Glen Fault, where the Loch Ness Monster is. So another link between Cape Breton and Scotland. Now again, you might say, so is there a place I can actually see this fault? Well, again, if you've driven around the Cabot Trail, you'll walk right over top of it, driven over top of it, and you've actually stopped at a roadside spot, but you weren't looking at the fault. You were looking at a big view of the North Aspy River Canyon. Here it is. So here's the Cabot Trail winding around, and Dingwall is way back in the upper right. You make that sharp right-hand turn as the Cabot Trail winds up to North Mountain, and you're crossing the Aspy portion of that Hollow Aspy Fault System. The action on the fault was this way, strike-slip fault system. And as I mentioned, at one point you were probably standing in a little turnoff right there and looking out across the North Aspy, but if you turned around and looked behind you, here you're actually looking into the rocks of a massive strike-slip fault system, and you can see the vertical orientation on these systems. Now, you might also say, well, if we had mountains, but they're much higher out in the Rockies, so did they reduce, or why aren't they quite as high? Well, there's over a couple 100 million years of erosion that eroded the mountains down, but yes, there are two other reasons why we don't quite still see the amount of relief that we used to have. So one's called infilling, and the other one is flooding. So let's see if we can give you a handle on that. We're going to take you now to the Middle River Canyon. The example out in the Rockies is Kicking Horse Pass. So here the mountains are quite high, but they're being eroded down. Those streams and rivers are bringing that eroded sediment down and filling in the valley through these big braided river complexes. In terms of the Middle River, here's an oblique aerial view. You can see the Middle River winding down. The upstream part is to your upper right. The Lake of Law is up to your upper left there. And lots of times people just see this, that's the river. It's never moved. Well, that's not right. See if we can give you a handle on that. So if you look straight down, let's say at a Google Earth image, you can see the Middle River winding its way up in blue. But what we want to do is to strip off that vegetation so we can look at the details, the topographic relief in this black and white digital terrain image. So let's load up the Middle River, and we'll load up the Cabot Trail. Now, both to the right and left in those highland areas, you might get 1, 2, 3, maybe 4 meters of material that overlies the bedrock. But we did some geotechnical drilling in this area. So the yellow indicates how that valley has been infilled as the river over the last 10,000 years since the ice left meandered back and forth and gradually brought sediment from the mountains down and filled up this valley. To give you an idea of the depths, we did some geotechnical drilling here. This is where the Cabot Trail Bridge running over the Middle River got wiped out a couple of years ago. And here, when we were doing the drilling to try and find the support for the new bridge, we were down 75 meters and still didn't hit bedrock. So you can see infilling by rivers will diminish the relief. The other way that the relief has been diminished is by flooding. So 9,000 to 10,000 years ago, when the ice left Cape Breton, sea level was about 50 meters below where it is right now. As a result, the Bredor Lake that we know was just a series of small freshwater ponds like we see here. Just so that you can get some reference where you're at, we'll show you where Eskazoni, Badek, and Waikagama are. As the ice sheets retreated, the volume in the oceans increased, and somewhere around 6,000 years ago, sea level rose high enough so that it started to flood in to the Bredor Lake and create what we now know as the Bredor Lake. So by flooding has removed an awful lot of the relief that we used to have. To give you some idea of the amount of that relief that we've lost, we'll load up the bathymetry, or the depth of water in the Bredor Lake. The dark blues and purples are the deepest spot. The oranges and reds and yellows are the shallowest spot. So here, the bottom of there is like 230 meters below present sea level. If we look in the Badek area, here you can see old river channels running past Badek. They're 25 meters below sea level. Here are a whole bunch of sinkholes. They're about 65 meters below sea level. And this old freshwater lake is about 105 meters below sea level. So you can begin to see the amount of relief that we have lost on the island due to infilling and flooding. To put it together now, we have 10 mountain regions in the UN Biosphere Reserve. The white areas indicate everything that's over 100 meters above present sea level. The blue areas indicate everything that's over 200 meters above sea level. So those ones greater than 200 meters that are big areas, Cape Breton Highlands, Gerlach Mountain, Waikagama Mountain, the Boisdale Hills. The smaller ones, over 200 meters, include Kelly's Mountain, the Craignish Hills, and Marble Mountain. And some of the white areas include South Mountain, the East Bay Hills, and Cairns Mountain. So we do have mountains in the Biosphere Reserve. Okay, so hopefully that answers the first question. Now let's get on to the second question. Why are they important to us as water towers? Okay, so now we need to begin to understand how the rocks talk to water. So here's a view from a fixed-wing aircraft. You're looking over Eskazoni to the north. East Bay is on your right. And over on the left are the Boisdale Hills Mountain Water Tower. And when you're talking about mountain water towers, there's two things to consider. One is what's called the mountain block. This is the big top of the mountains. But then there's also the steep transition slope, which is called the mountain front. And then you have the adjacent lowland areas. There's some definitions you may want to write down. Okay, once you've got that, let's look at Cape Breton and see how all that fits in. So if we load up the Biosphere Reserve watershed, and then we load up all the areas greater than 100 meters above sea level, we get this. But if you remember, I said there's a mountain block, that's the upper part, but there's that steep transition slope that's also part of the mountain water tower. And what I've done here is taken all the slopes greater than 20 degrees. So there's the mountain front. So quite extensive mountains in Cape Breton, Unama'ki, and in the biosphere. So the first thing we have to understand, if we want to call these mountain water towers, is that they collect and store snow in the winter and then gradually release it in the spring. So let's take you to the Cape Breton Highlands Mountain Water Tower to try and explain that. So this is a NASA satellite image. So in the late fall, we get these large low pressure systems. So the winds come in from counterclockwise circulation. They come across the open waters of the Gulf of St. Lawrence. They pick up moisture, so there's no ice there yet. They hit the highlands, they raise up, they cool down, and they drop precipitation as snow. And as long as there's no ice over the Gulf of St. Lawrence, this process just continues. Once ice starts to develop, then it shuts down. But we're getting less and less ice in this Gulf. Matter of fact, there was very little last winter. And so that snow belt just keeps building and building and building. To give you an idea of that, we'll just take a few NASA satellite images from the Aqua and Terra satellites. Give you a rough idea. These are from a number of different years. So December, you can see the snow belt starting to build up in the northern part of the Highlands Water Tower. January, the whole island is covered with snow. February, ice pack is starting to build in this particular year, starting to shut down the development of the snow in that mountain water tower. Early to mid-March, well, you can start to see the snowpack melting in the lowland areas, but you can still see snow up in some of those mountain water towers like South Mountain, North Mountain, Boisdale Hills, Kelly's Mountain, and the whole west coast of the island. Late March, well, the snowpack is pretty much gone a lot in the lowlands, still really prevalent in the highlands. Mid-April, snowpack's still up there on the mountain block, but you can see some of the lowland canyons like the Northeast Marguerite and the Cheticamp, they've already started to lose their snow. Late April, snowpack still there. Early May, snowpack still there. Early June, just a slight hint. So you can begin to see how that snowpack lasts over these mountain water towers. Now, to give you an idea of how that holds and then how that melts, that's also important. So this is what the snowpack looks like on the Cabot Trail in North Mountain at the peak of the snowpack. And I've created a little bit of a graph here. So on that lower horizontal axis, that's time going from October the 1st on the left through to June the 1st on the right. And that vertical axis shows the depth of snow from 50 centimeters up to 250 centimeters or 2.5 meters. So what I did was they record at certain Environment Canada stations the depth of the snowpack once a day. So if we did that for a lowland station in around Sydney, this is what we'd see. So you can see the snow starts to build up in around January, late January, early February, peaks in around early March, and then drops off quickly. So by, the 1st of April, it's pretty much gone. But it turns out there's an Environment Canada station just over the crest of this hill. And if you show the snowpack for the same year, this is what you get. Quite a difference. So the snowpack starts building up in late November, rises slowly, peaks in and around March and April. And the reason it's flat top there is that the depth of snow exceeded the snow gauge, so it inundated the snow gauge. And then it gradually melts through April and May and into June. So for the lowland populations, it just creates this slow snow melt, which enhances flows in the rivers. The other thing to remember about these mountain towers is that even when it's not collecting snow, it can bump off an awful lot of rain. And so it can do damage to our infrastructure in the lowland areas. So this is the Cabot Trail Bridge. We're going over the Middle River that got wiped out a couple of years ago. So we have to watch these mountain water towers in terms of damage they do to adjacent lowland infrastructure. But the other thing you have to keep in mind is sometimes people just look at the Middle River like this and they say, well, there's the channel now, it's never moved. Well, the whole valley floor is infilled with all that material I mentioned. It's all loosened sand and gravel, so the river can easily migrate back and forth across the floodplain. You can even see some of the old channels here. So if you own property along some of these rivers, you just got to be careful, because if the river decides to change its course, you may not have that property. Or if you build close to the river, well, it may get eroded out. Now, these mountain water towers also supply water to municipal groundwater well fields. So we'll use Eskasoni as an example. Here's that same picture. Here is the mountain front. Now, in this case, it's really underlain by a fault zone. It's not structurally active, but it's hydraulically active. The rock have really been ground up, very high permeable. So we've developed 3 groundwater well fields that supply Eskasoni. And the water coming off the mountain block up in the upper left is feeding those, as well as that fault aquifer. Those mountain blocks can also create quite a number of springs. A good example here is in Rear Badek. So here's that mountain front again, heavily fractured fault aquifer, and it's pumping out at least 30 different springs that we've found. And these springs contribute flow to the Badek River. As a matter of fact, one of the largest springs we found on the island are shown here. So these can be pretty substantial, over 500 US gallons a minute coming down there at certain times. And they feed, as I mentioned, flow down into the Badek River. And some of these particular springs have quite unique ecosystems associated with it. And these can form because there's groundwater coming out. It's usually cool and stays the same temperature year round. Chemistry stays the same, a little bit of fluctuation in discharge, so it forms pretty unique habitats. Of course, mountain water towers also provide us with fishing fall colors. We'll take you here to the northeast Margaree River Canyon and a beautiful fall day. So that the Cape Breton Highlands mountain water towers in the background, the steep transition slopes here, and it's those steep transition slopes that are beautiful habitat for Acadian dominant hardwood forests, which change color and make it such a beautiful spot in the fall. And of course, the fall salmon runs. If you looked here, you can see salmon fishermen, and a lot of that water is coming off those mountain water towers. Hydroelectricity, well, we have the Wreck Cove hydroelectric development up in the Cape Breton Highlands mountain water tower, which provides power to the provincial grid. Forestry, well, a lot of those mountain water towers, because they're remote, there's forestry activity going on. We'll show you here in the upper headwaters of the Bador Biosphere. So, and the Leahy report recommended this with one spot for large-scale forestry operations. The question then becomes is, what impact do those forestry operations have on how the water moves off these mountain water towers? Mining potential, well, if you're looking at the roots of those old mountains with those big granitic batholiths and faults, metamorphosed rock, they can form great areas for mineral potential, shown here. Finally, recreation. Well, if you load up all the provincial parks and all the federal parks, where are they? Well, they're sitting, most of them are sitting over top of these mountain water towers. Okay, so hopefully that's answered the second question. Why were they important to us? Third and final question is, okay, so what are we doing to better understand them? Well, one of the research initiatives is here at Eskasoni, the Boisdale Hills Mountain Water Tower. And it's a combination of a number of folks, Eskasoni Fish and Wildlife, Bador Lakes Biosphere Reserve, Dalhousie University, and myself. And what we're trying to do is to get a handle on how the water on top of the mountain block, such as here at top of the Boisdale Hills, with their vast wetlands and boreal forest, how does that get down to the lowland into that mountain front? So if we take a different view of it, looking from the bottom up, that shot we just saw is in the background. The Christmas Brook that's being monitored runs from the mountain block right down to the Bador Lakes and right through the mountain front, which is that fault aquifer that Eskasoni is drawing water from. One of the well fields is here at Arena Road. So the concept is, how does that water from the mountain block get down to the mountain front? Is it feeding the water that those wells are drawing from? If so, how old is that groundwater? How does the surface water impact the well field? So that's a research program that's going on. We can begin to understand the answers to those questions. We can then extrapolate it to other areas in the biosphere. There's also a forest hydrology research program going on, which is a combination of First Nations, UINR, Oceans North, Port Hawkesbury Paper, Natural Resources, and EXP Services Incorporated. And our one site is down here at Irish Vale on the East Bay Hills Mountain Water Tower. So they forested this area back last fall. There are streams draining out of that forest area going down into Irish Vale Brook. And the question we're trying to answer here is that a lot of times the impact of forestry operations has been looked at, what's the impact right there, right where they did the forestry? We're trying to look at, well, could those impacts be moved off-site through groundwater and streams? So if you look at these very narrow, low-order streams that are sitting up on top of the mountain block, where they would first pick up the impact, the big question too is that those streams run down through these steep gorges and ravines. Do those gorges and ravines, which aren't forested, did they somehow or other act as a treatment system or a buffer system to handle any impacts coming through it? Stream flow monitoring. Well, there's a joint federal-provincial agreement. So there are for establishing gauging stations on certain streams that continuously measure the flow coming through it. So in the biosphere, we have 2 such stations. The oldest is on Middle River, which drains the Cape Breton Highlands Mountain Water Tower. So for example, if you're looking at the gauging station, looking downstream, this is what it looks like at low flow. This is what it looks like at high flow. So by looking at those flows, we can see how flows are starting to change, either because of the operations going on up there or changing climate. We can begin to see the changes in chemistry and, for example, here in suspended sediment load. The Bador Institute with Dr. Bruce Hatcher is working with Dalhousie University trying to understand the dynamics of the Bador Lake itself. One of the things that they're looking at is the current movement and the chemistry of the water. And one of those is to look at stream flow coming into the lake at low flow here or at high flow. So they have equipment that they measure that flow in on very smaller rivers. Well, you've probably heard about the Cape Breton Mesonet under Jonathan Buffett's guidance. And this is a good example of citizen science that's helping us to understand these mountain water towers. So we've got 22 sites. And because we have so many sites, we can begin to see the microclimates that are being developed. Aquatic ecology. Well, we have First Nations, Cape Breton University, a number of spots where they're doing what are called cabin programs to understand the aquatic ecology of these various rivers and streams. And they have a smolt wheel on the Middle River to try and assess salmon movement and track them to see how they're moving in and out of the Bador. Dr. Jim Foles and myself have been working on developing a salmonid management zone along with Georgia Pacific down here at Melford. So we now have a little over 20 years of data on this particular river, which is known as a fairly large salmon habitat. So we've done electrofishing, actually sent some away for the viruses that are developed in them, and we have, let's say, a little over 20 years of stream flow and chemistry. So we can end up better understand how these systems work. And if we can understand how it works in this particular hydrologic setting, we can extrapolate it again to other areas in the biosphere and throughout Unama'ki. Of course, when you're in this brook, you also begin to recognize that there are other life forms that are quite interested in how these mountain water towers affect stream flow, such as beavers. And it's amazing the dams they can build. Now, my wife and I started developing a program for monitoring freshwater resources all over the island. And within the Bador biosphere, we are presently monitoring 1 wetland, 4 Baechler ponds, 3 vernal pools, 12 springs, 6 wells, and 11 rivers to try and give us a better understanding of how these mountain water towers work. All right, well, I've hit you with an awful lot in a short period of time. So in terms of conclusions, I'm going to leave you with 3 take-home messages. Your background slide here is the upper part of the Middle River as it's down-cutting through the Highlands Mountain Water Tower on a beautiful fall day within the Middle River Wilderness area. So those 3 take-home messages are: 1, yep, we do have mountains in Cape Breton, Unama'ki, the UN biosphere. Yep, they do act as water towers, which are important to us in many ways. And finally, yes, we are working at trying to understand them better. We have a lot more work to do. And there's a lots of room for citizen science and to those folks that are working on trails to get people out into these mountain water towers. All right, folks. Well, thank you very much for your time and good luck on your test. Take care.